hopefully that was somewhat interesting, but all things considered, I don't think that was the greatest introduction to two-dimensional Riemann sums, but I do think it was pretty good in conveying some of the things you can do with monocurl. So let me just kind of run down some techniques I used. I won't go through everything, and source code will be available, but more so just some of the tricks and general concepts. Okay, so in the config side, that's typically where you want to keep constants that are good for determining the full outcome of the scene, as well as useful constructs that you're going to be using. So for me, I just did some text specializations just because we had a decent amount of text. I think these ones in particular are quite nice because the default text doesn't allow you to specify location. Also, weight 1, that's used a good amount, helpful for timing. Okay, the actual interesting one though is this thing called transfer transform. I'll talk about it more when we use it, but the idea is usually when you just perform a transfer, it's going to be instantaneous. So when we actually want to do something more continuous, this is going to come into play. All right, the actual title slide is pretty simple. It's just a fade out, so I won't really go over that. And this one, while it might look fancy, it's just some text and writing it, so actually not too bad. For the next slide, again, not super complex stuff. The only thing I will point out is that for this integral, we did have to do some work to make sure that the pins were set up correct, which is just tags, just so that when I'm doing this transform, we get that the A transfers into 0.5 and the B transfers into 4. All right, from here, again, just setting A, fading it out. Nothing super complex, but starting from slide 5, we do get into the main meat of things. All right, so now that we've seen the entire video, we'll notice that there's a few different things that we want to do over here. So I kind of want to have all of that behavior encapsulated within the function we use to create it. So in particular, we first want to be able to make a stem plot, but then later on we're going to have to use rectangles, and then even more later on we're going to have to use trapezoids. So it'd be convenient to have all of this in the same function so that we can very easily interpolate or transfer between them. So this node class is just going to tell us, or it's just going to give us the actual represented symbol, and then this stem, this functor, is going to actually help us create a collection of them. So the node is just an individual stem or rectangle or trapezoid, and then the stem is just going to be the entire collection of them. Other thing to point out is that for every single one of these objects, the tags are set up correctly. Again, 0, 1, 2, 3, 4, the obvious tag. And the actual dots are tagged slightly differently. They're going to be tagged with negative numbers. So this allows us to identify which of the objects in the mesh tree are going to be dots and which of them are going to be the actual stem, rectangle, polygon, or not polygon, sorry, trapezoid. But as we start out, we're just going to have it be at the very bottom. Right, we're just going to have the dots, and then we want to grow that in. So to actually do that, we can just do a lerp, and we'll lerp the height from 0 to 1. I actually call it y, but not a big deal. Okay, and then to actually do this transform, this is just going to be a simple tag transform. Okay. The next part is a bit interesting as well. So how we're going to do this is we're going to basically fade everything out. That's what's over here. We're going to fade everything out. And then for fade everything out except this and this. So the objects in focus. And the way to actually make sure that we fade everything out except some subset is basically just to use a mesh select, which is going to allow us to select some subset. And it's going to, in particular, allow us to select the subset that we actually want. Okay, so this process is a bit complex, and as a reminder, what we're focusing on right now, what we're focusing on right now is this scene. So to do this, I'm gonna have a helper functor, and then this helper functor is gonna be very useful because it's just gonna provide this stuff and this stuff for us. So all we have to do is just change the index. And if we change the index, it'll now move for us. That's great, but we also want to have that animation where this f of 0.5 and this delta x gets transferred to the equation. Okay, so how are we going to do that? Well, we already have a way to move this from here to here. We can just do that by changing the index of this functor, and it'll handle things for us. Again, I'll probably not go into details too much just because that's not super complex. So we can move that to the right pretty easily. But to actually move the value from here to here, so let me just play that like that. What we want to do is to use the transfer transform that I was talking about before. So in particular, we're going to transfer it. The destination is going to be the definition because we basically want to transfer it from the measuring device into the definition. And then the source is going to be the measure. And then the predicate is just going to tell us that we don't want to transfer everything, right? We don't want to transfer this bar, for example, the measuring bar we don't want to transfer. We just want to transfer the text. And then the target is going to be, well, we don't want to transform it into the entire text. We just want to transform it into this specified subset. So once I have all of that, then the transfer is going to look pretty nice. Okay, and then maybe we could just scroll to how we actually do it. So to actually implement this transfer transform, sorry, that's a bit hard to say. To actually implement the transfer transform, we're going to do a very common pattern in monochrome where we'll first transfer it to an auxiliary variable. And now that it's in an auxiliary variable, we kind of have complete ownership over the auxiliary variable. So the auxiliary variable is very easy to animate. So we transfer it to the auxiliary variable, which we now have full control over. We're going to set the auxiliary variable to the target, which is specified. That's going to be this guy. Then we'll transform it into the target. I do a tag transform just so that we can make sure that this goes to here and this goes to here. And then now that the auxiliary variable is in its final state, let's transfer it to the destination. So let's transfer it to this text for the measuring. And that might seem a bit complex, but this is a pretty common pattern in monochrome. But definitely remember this auxiliary variable. That's going to be common a lot when you want to make more complex animations. So hopefully, even if that did seem a bit involved, the ideas should seem simple. And I think that's just a common pattern in monochrome where even if the idea is somewhat simple, it might just have a high learning curve. But I think once you get it, it does become a bit easier. All right, so now we just do all of that in our for loop. And we can go through every single one. Nice. Okay, and then also note that I saved the state because whenever we were fading everything, it became faded, but now we want to restore state. So I save all of the variables, and then we're restoring state. Okay, so then the next part is how do we make it so that we originally had an LRAM and we want to make it an RM. Well, this is again pretty easy. It's just a lerp on the interpolation factor, and then also the changing the definition text. Again, one thing I don't like about monochrome in the beta release at least is that text is not well done. So for now, the easiest way is just to write a bunch of pins. Pins are for giving a specified text in LaTeX a certain tag. But yes, this is pretty tedious. I will think about ways we can improve this in future releases, but in the beta release, that's probably the easiest way to do things. But do note that this shows another importance of functors is that we kind of had to think somewhat far into the future. I say think far into the future. More likely than not, it would be that once you go into the future, you realize that we have to do this animation of the dots from here to here, and then let me add in that capability into the functor. Okay, so that's probably how I would go about things, is initially just have the functor have the minimum capability, but then later on I realize, hey, I need to do this interpolation, so then I'll add in this factor of mid, for example. And just to put one more point on that is that I was originally thinking of, hey, maybe I want to have an animation where I increase the number of rectangles, so that's why I have this n. But I ended up not doing that. But now it's very easy to do it if I wanted to because it's a parameter, and parameters are very easy to learn. Oops. Okay, next one, just changing it to a trapezoid. Again, same idea, we're just going to change the type and then do a tag transform. So that part's actually not that bad. Okay, so now the next thing, slide 10, is actually going to be representing the formula for the kernel. Honestly, I probably should have had somewhere actual text showing the formula for a trapezoid, but I didn't. But anyways, the actual kernel is going to be pretty simple. We're going to have two sort of things. So I have two kind of ideas for a kernel. One, we'll have a kernel that's going to be our entire builded section. So the kernel we can just think of as a set of dots, or a set of line of dots. I'll just call it that from now on. We have this line of dots, and we have one that's the entire builded image, and then we have this other one which is what's actually moving around. So we can actually, because they are somewhat similar in nature, we can kind of reuse the same functor for both of them. And what I'm going to do is we have one tree for the total and then one tree for the marching section. And then from here, it's just a bit of bookkeeping to make sure that we get all of the states right. But if we do, then it's just going to be a simple set and transform. Okay, over here, we have to fade out a lot of stuff. I am possibly considering in the future having it so that set, follow, transform, all of that can automatically detect the iterators that have changed, and then the follows will change correspondingly. I haven't done that for the beta release, and there are some downsides, but I will consider it. But yeah, for now, you will just have to write out all of the things, even if it's ever so slightly redundant. Okay, from here, we actually get into the 2D case now. Okay, so from the 2D case, honestly, the idea over here to the 2D case is relatively straightforward, or I wouldn't say straightforward, but it's a relatively similar to what we have over here, except now we're just generalizing to 2D, right? So what I want is, I want to have a field of points. I want to have a field of points. Over here, we were able to just get away with having all of the things in a line. But once we get to more complex layouts, it is helpful to use some of the built-in functionality for placement. So in particular, we're going to have a field of points. That's going to be our mass. That's like the built image. And then in addition to that, we have to have this moving kernel. So over here, I decided that they're different enough that I'm going to separate them. All right. Okay. And then from here, again, it's not super difficult logic. It's just a bit of bookkeeping. But basically, the idea is I'm going to go through every single possible state, and then we'll just transform it. A lot of the stuff over here is just about, well, when we're in the torus case, we don't want to march it over here, for example, because a lot of the points are disabled. Okay, another point I will like to make is that the code over here for marching the kernel on the square is pretty much the same as marching it on this torus or the donut. So we can actually make that an animation, we can make that animation a function, and we can reuse that function over here. So functions, animations as functions, is useful to abstract logic like we saw in the transfer transform. But it can also be useful if we're repeating code a lot. And again, it provides a very simple interface. But usually, if I'm not in either of those two scenarios, I'll usually just write out the thing like I did over here, where even if there's lots of animations, I'll just have it pretty much in the global playlist. But I think that's just a matter of preference. All right. Yeah, probably not that much more to say for here. Yeah, so that's the other nice thing, is that we can reuse stuff. So the generalization to the torus is actually very simple. We just have to mark the points that are disabled, and then we can reuse exactly what we had. All right, the final set of animations is we first want to convert this into, instead of a set of dots, we want to have this as a color grid, right? We want to have every single square has a color based on the function. So that's one thing. What I just did was I faded out the mask and I faded in the color grid, but not too much complicated stuff. The only thing that is slightly complex is we have to actually map it up, but that's pretty easy using a point mapped, right? So we did point mapped, and then that's good. Okay, and then the final job is we have to kind of do the same thing that we were doing above, where we're going to be marking a kernel, but this time the kernel, instead of being a square, it's a more complex object. And it's somewhat the same level of code, so I won't dwell into things too much. But one thing I will point out is that by default, the alpha rendering isn't great, so sometimes you will have to manually help out in getting the order correct, which is what I do over here. But otherwise, it is more or less the same things that we had previously. All right, and that's pretty much the entirety of the scene.